Welcome back, fellow night owls. In this video, I'm continuing this project of going through the written answer exam questions from past LTAMs. This is from fall of 2020, and this is question number 2. To my mind, this is just about the easiest question of the written answer questions on this exam. So let's get to it. It says, consider the following expression for the force of mortality. Mu sub x plus s equals alpha e to the lambda x plus s. All right. And first question is, show that as long as alpha is positive and lambda is positive, tpx, the probability that x survives t more years, equals e to the big brackets negative alpha e to the lambda x times e to the lambda t minus 1 all over lambda. All right. So we'll start with hopefully this familiar formula that the probability that x survives t more years equals e to the negative antiderivative from 0 to t of mu, the force of mortality, dx. If you don't know where that comes from, that's just briefly outlined here in gray. Definition of mortality equals rate of decrease of survival divided by the number that have survived up to that point, and just using some basic differential equations that you might have seen in AP calculus if you took that. You just get mu equals negative ds dt over s, multiply by dt, mu dt equals negative ds over s, integrate both sides. You notice that integral of ds over s is natural log of s, so you get mu dt equals negative ln s, e to both sides, and you get s equals e to the negative antiderivative of mu. Okay. So we have this formula. We just plug in our function. Mu equals alpha e to the lambda x plus s. Now we notice we're only anti-differentiating with respect to s, not with respect to x, which means we can pull that x stuff out. So we pull out all the constants that we can. We'll pull those out of the integral just to simplify it down. E to the negative alpha e to the lambda x. Notice this is matching what we want it to match. It's that times integral from 0 to t of e to the lambda s ds. All right. Antiderivative of an exponential is just itself divided by whatever constant you need up here. So it's going to be this times e to the lambda s over lambda, evaluated between s equals 0 as the lower bound, s equals t as the upper bound. So upper bound is going to be e to the lambda t. Lower bound is going to be e to the lambda 0, or 1, right? E to the 0 is 1. So final answer, we get e to the negative alpha times e to the lambda x times e to the lambda t minus 1 all over lambda. Exactly what they said that it was supposed to be. No big surprise there. Next, in the special case where lambda equals 0, clearly we can't do it this way because we would end up dividing by 0, which never quite works out the way you planned it. So instead, we just point out that if lambda equals 0, then our mortality function simplifies to alpha times e to the 0. Right? If lambda is 0, this just all cancels. Alpha e to the 0 is just equal to alpha, because e to the 0 is 1. And tpx, using the same formula, is going to be e to the negative antiderivative from 0 to t of alpha ds. That's just going to be e to the negative alpha t. Not too bad. Next, state the 3 conditions that a survival function must satisfy in order to be valid. So, condition 1, everybody survives at least to the beginning. S sub x of 0 equals 1. Number 2, no immortality, unfortunately. S sub x of infinity equals 0, or if they're making you do it precisely with limits, limit as t goes to 0, limit as t goes to infinity of s sub x of t equals 0. And finally, there's the no zombies condition. Once you're dead, you pretty much stay that way. So that means if time A is greater than time B, then you needed fewer people alive at A than you had at B. All right. And so now for part B2, we just have to show that for our original function, where the survival function is this, just copied from what we had previously, show that this satisfies the necessary conditions. So first one, we plug in t equals 0. All right, that means that this e to the lambda t becomes a 1 because t is 0. We have a 1 minus 1 that goes to a 0. We end up taking exponential of 0 because this 0 multiplies by everything else here. E to the 0 is just 1. And so that's satisfied. Next, show that if t goes to infinity, that this whole thing goes to 0. All right. If t goes to infinity, then we have an e to the infinity here. That's going to make everything here go infinite. We have a negative sign here, so it's going to be e to the negative infinity, and e to the negative infinity is 0. And finally, we have to satisfy the no zombies condition. And so one way to do it is just look at our function itself, say that, well, as t increases, this is monotonic increasing, gets multiplied by constant, so still monotonic increasing, gets multiplied by a negative, so monotonic decreasing. E to a monotonic decreasing function is also monotonic decreasing. Therefore, since it's decreasing, it satisfies the no zombies condition. If you wanted to do it more formally without pointing to monotonic increasing versus monotonic decreasing, just take the derivative. Make sure you differentiate with respect to t, not with respect to x. You're changing the time at which you're seeing how many people survive, not the age at which you assume people start at. So you take the derivative, properties of differentiation, a little bit of chain rule here, and you say, okay, it's going to be all this. This is going to be a positive number here. This is going to be negative here. You multiply them together, you do get something negative. Derivative is negative, therefore the no zombies condition is satisfied. Part 3, we just want to do the same thing for the simpler case where lambda equals 0. So now we have an even simpler function. This is, I've got it here in the red. Survival is e to the negative alpha t. Survival of 0 is e to the 0, which is 1. Survival at infinity is e to the negative infinity, which is 0. Again, we're assuming alpha is positive still, so it does work out that way. And finally, derivative with respect to t is just going to be negative alpha e to the negative alpha t, which is negative. So the no zombies condition is satisfied. And finally, for part C, says, roughly sketch the pattern of force of mortality for males under age 30 as seen in a typical population mortality study. All right, that's what I've got in blue here. From birth till around age 5, you've got what's called the infant mortality. That's where you're a tiny little baby, you don't really understand what's going on in the world, and you get stupid ideas like, oh, see that flight of stairs? Let me crawl down on it head first and hope that nothing goes bad, or nothing goes wrong. Then, meanwhile, stuff behaves relatively normally of low mortality, slowly increasing until about age 15, when you start with what's classically called the accident bump, that I tend to prefer calling the recklessness bump. That's when you do stupid stuff like getting really drunk, looking outside your window at the 4-story drop to the pavement below and saying, hey, I can make that jump. So you briefly have some increased mortality there as you start doing stupid stuff because you're a stupid teenager. You get to age 25, you're no longer a stupid teenager, and your mortality reverts back to its more natural physical laws. So the blue curve does that. Meanwhile, you look at the red curve of this, you just go back to the mortality function they gave you, where it's some constant times e to something involving x and s and how it's going to be. The important thing is it's increasing in concave up. So at absolute best, it would kind of be doing this, but that the red curve is doing, but it would skip the infant mortality and it would skip the recklessness bump. Given that the infant mortality occupies about 5 years and the recklessness bump occupies about 10 years, those combine for about 15 years. That's half of the time that they're interested in, which is 0 to 30, or it says males under age 30. So because This model does not accurately account for the infant mortality and does not accurately account for the recklessness bump. And I would add, chances are most of the deaths of people under age 30 would probably be accounted for under those two things. That's what they're getting at, right? That's why you really can't use this for this age range. All right, as I mentioned, this was the easiest problem, easiest written answer problem on the exam. And as always, if you like my way of explaining things and wanted to arrange private lessons, check the link below. And until next time, this is Dr. Nighttime wishing you a good night.